Hello, welcome back to another video. Today we're going to be looking at the rates of reactions from this past paper. Question 1.5 reads, consider the potential energy graph for the reaction shown below. The activation energy for the forward reaction in terms of P, Q, and R is. Okay, let's try. So we know that activation energy is going to be the energy required for a reaction to occur. So let's quickly just do some labeling here. We know that this is going to be the energy of the reactants. This is going to be the energy of the products. Right? And since it is a forward reaction, then we know that we're reading it this way. Now, activation energy for this reaction is going to be from the energy of the reactants to the activated complex, which is this top region here. So this line that I'm drawing represents the activation energy for the forward reaction. And so we can work it out by saying Q minus P. Okay, so that difference in height. And so the answer we will go with is D. Okay, let's move on to the long question. Question 5. Two experiments, 1 and 2, are conducted to investigate one of the factors that affects the rate of the reaction of aluminium carbonate with excess hydrochloric acid. The balanced equation is given. They're also given us the apparatus. We can see that there's hydrochloric acid that's being dropped into this beaker with aluminium carbonate. What we also see is that there is a syringe here, and that syringe is there to collect gas. So the gas will form and fill that syringe, and that syringe will then open and expand, and that's how you'll get the volume of gas. Now, what gas are we going to be collecting? If you look at the products, you see that you're forming aluminium chloride, you're forming water, liquid, but you're also forming CO2 gas. So the gas that's going to form in here is CO2. Let's move on. The question reads, the reaction conditions used for each experiment are as follows. Experiment 1, 100 cm cubed of 1.5 moles per dm cubed HCl reacts with 0,016 moles Al2CO3 granules at 25 degrees Celsius. Experiment 2, you notice that the concentration is different. Okay, but the number of moles is the same. The state of division is the same, granules, and the temperature is the same. So you'll notice that these are the same. And what they're changing is they're changing the concentration. We'll leave out the definition. We're moving on to 5.2, which reads, using the experimental setup above, state the measurements that must be made to determine the rate of this reaction. Now, rate of reaction, we know that rate means how fast it's occurring. So that means for 5.2, to measure how fast something is occurring, we need to measure time. So the first thing we're going to measure is time. And the second one, we said that there is a syringe, and that syringe is going to collect gas. And so the second thing we're going to be collecting or measuring is the volume of CO2 gas that is produced. Okay, let's move on. Question 5.3. Use collision theory to explain how the average reaction rate in experiment 1 differs from the average reaction rate in experiment 2. We can see that in experiment 2, there is a higher concentration than experiment 1. So what we can do is we know, let's write this out, 5.3. One of the factors that affects rate is concentration. And we know that if the concentration increases, the rate of the reaction will also increase. Now, using collision theory, we need to explain why this is so. If there is a higher concentration, so experiment 2 has a higher concentration of HCl. That means there's more particles per unit volume. If there's more particles per unit volume, there's going to be more effective collisions per unit time. And if there's more effective collisions per unit time, that means it's going to be an increased rate of reaction. So experiment 2 will occur faster. Okay, let's move on to question 5.4. The average rate of the reaction in experiment 2 during the first 2.5 minutes is 4,4 times 10 to the negative 3 moles per minute. Calculate the number of moles of Al2CO3 that remains in the flask after 2.5 minutes. So if we read the information that's given to us, they tell us that in experiment 2, they start off with 0,016 moles of aluminium carbonate. So the amount of aluminium carbonate that's going to be left over is going to equal the amount that we started with. So 0.16 minus the amount that's used. Now we don't know the amount that's used. However, we've been given the rate of the reaction, and we can use the rate of reaction to work out the amount that's used. All right, so let's start. So first we will say that the rate of the reaction is equal to, in this case, it's going to be moles divided by time. The rate is 4,4 times 10 to the negative 3. That's equal to the number of moles divided by 2.5 minutes. So we cross multiply now. That means the number of moles is equal to 4,4 times 10 to the negative 3 times 2,5. 0,011. 0,011 moles. And what is this the moles of? Remember, what was being measured? We were measuring the volume of CO2 gas that was produced. So this moles, this is the moles of CO2 gas produced in 2.5 minutes. Now, once we got this, we can use a mole ratio to work out the moles of aluminium carbonate that was used up in that 2.5 minutes. Now we'll do a mole ratio. So Al2 CO3 3 to CO2. Now we get this from the reaction. It's 1 to 3. So 1 is to 3. Now we know that the amount of CO2 is 0,011. And that means to get this, we divide by 3. So that means the amount of Al2 CO3 3 is equal to 0,004 moles used. Now that we have the amount that's used, we can go back to our original and say 0,016 minus, here's the amount that's used, 0,004, and that gives us an answer. So we'll say 0,016 minus 0,004. So after 2.5 minutes, we are left with 0,012 moles of aluminium carbonate. Okay, let's go to the last question now, question 5.5. Calculate the maximum volume of CO2 that can be prepared at 25 degrees Celsius in experiment 1. Take the molar gas volume as 24,000 cm cubed per mole. Okay, so maximum volume of CO2 gas, and they're talking about molar volume. So that must mean we must be using the equation N equals V divided by Vm. Now, Vm is 24,000 cm cubed per mole. Now, we can convert this 24,000 cm cubed divided by 1,000, you're going to get 24 dm cubed per mole. All right, now we know the molar volume, which is 24. V is what we want. That means we must be able to get the number of moles of CO2. Now, since we are talking about experiment 1, let's look at the information that we've been given. So experiment 1, they tell us 0,016 moles of aluminium carbonate. So what we can do is we can use a mole ratio. So again, aluminium carbonate to CO2, that means 0,016. So if you multiply this by 3, yeah, the mole ratio was 1 to 3. So that means 0,016 multiplied by 3. That means the amount of CO2 that can be produced is 0,048 moles. So again, if we start with 0,016 moles of aluminium carbonate, theoretically the maximum amount of moles of CO2 that can be produced is 0,048, because remember, aluminium carbonate is our limiting reagent. Now that we have the number of moles, we can calculate the volume. So 0,048 is equal to V divided by 24. Cross multiply, V is equal to 1,152 dm cubed of CO2. And that's it. If you found this useful, please leave a like, share, subscribe, turn on that notification bell. If there's something specific you'd like me to do or a question you may have, let me know in the comment section below. And until the next one, bye-bye.